Great, thank you, Cassia. And good morning or good afternoon, everyone. So I just want to kind of give a brief overview or partly history, partly just survey of spatial ontologies. This is by no way complete, but kind of just gives a taste of the different kind of spatial ontologies we're dealing with and how we use them. So let me start with kind of a simple example, something that a lot of practitioners might actually encounter, not so much like the more formal ontologists, like the use of spatial data in an ontology, like in a RDF data set, where we talk about some like features, like a school, for example, and its address on the right side here, and some location using kind of a spatial reference system. And probably that is what most people think of when they think of space, or they associate it with location information, like you can pinpoint it somewhere on the map. So while this is probably one of the most widely used kind of ontologies of space, it's not particularly interesting from an ontological perspective. We have the only distinction here between geometries and what we call features, like objects that are located in space. And this is actually kind of the pattern that geospatial and simple features, like two standards for spatial information on the web, for sharing information using RDF and code, and then you can kind of use that in your application as you kind of see fit. And that's actually widely used for all kinds of mapping applications, or where people contribute like citizen science information. For example, eBird here is like where you contribute like your observations of different birds, and they are just broken down to a point on a map, and then you can like retrieve all those points again. And it's supported by a lot of databases. But as I said, it's ontologically not particularly interesting. So let's maybe go back a little bit in history. So what is one of the oldest ontologies of space that we can think of? And there's something that we all encountered in, I don't know, middle school, high school, geometry, Euclidean geometry in particular. It's one kind of axiomatization or conceptualization of space that most of us are familiar with. And it consists of a set of axioms, like assumptions that we make about space. And this is kind of one way of looking at space from an axiomatic perspective, like collecting statements that we assume to be true and then analyzing them based on what additional consequences follow from these axioms. So kind of looking at Euclidean geometry as kind of an ontology, a spatial ontology, we can look at the kind of object it talks about and the kind of spatial relation it talks about. So what we call, like in an ontology, as the logical primitives, like the classes of objects, points, straight lines, planes, and then the primitive relations. So Hilbert's axiomatization of Euclidean geometry uses like containment, betweenness, like a ternary relation, and congruence between line segments and angles. And then you have kind of axioms such as for any 2 points, there exists a line that contains both of them. And this is something we can actually debate we can like say, is that something we want to be true or something that we need to be true? And what other things follow from that? So do we actually want the parallel postulate that for any line L and a point A not on it, there is at most one line in the plane? And these kind of considerations that we deal with in formal ontology or applied ontology all the time is what actually led historically to the development of alternative geometries. So the point here is not like to bore you with geometry, but to kind of draw the analog between what we do in spatial ontologies or ontologies in general nowadays and what has historically happened. So that's what led to elliptic and hyperbolic geometry, and eventually, like we see that in Hilbert's axiomatization, also like a modularization of ontologies, like teasing out what can we do with only incidents or only incidents in betweenness, but without congruence. And these are the kind of questions we asked ourselves in spatial ontologies as well. Likewise, kind of questioning some of these assumptions, we can also question the choice of primitives. So are points actually suitable primitives or not? And this is what historically led to the development of point-free geometry, starting with Whitehead. And most of you have probably heard of mere topology, which has kind of originated from this area of point-free geometry. So the idea there is that a lot of space is not necessarily geometric, like especially when we talk about space every day. We talk about it in a relational way, like I'm parked in the far north end behind the supermarket, or the key is in the left coat pocket. Walk along one block along Main Street and then take a right turn. The bank is on the left side right after the park. These are spatial descriptions that do not use any geometric information. And so kind of a sub area of spatial ontologies and an area called qualitative spatial reasoning has kind of looked at some of these types of qualities that we care about in space, like connection parenthood, which constitute mere topology, but also others like orientation, like north-south, left-off, order between spatial objects, and relative size, distance, proximity, etc. So the biggest amount of work that has gone into developing qualitative ontologies of space has focused on mere topology, starting with the region connection calculus by Vander Curry and Cohn, which tried to start with a single relation and primitives being regions rather than points. So the object of interest are region, and then we're trying to formalize like what other relations can be defined or constrained using axioms. So for example, here for the RCC, the undefined relation is that of contact, and then we define things like parenthood, overlap, external connection, etc. And then we can actually test the consistency of certain data sets, whether certain statements are consistent with one statement or not. So for example, if we have a statement like if a region A is part of a region B and A overlaps another region C, can B and C be disjoint? And if you try to draw this out, and it here on the right-hand side, you see this is not possible, but you would want our axiom to actually tell us that this is not possible. So the definition of parted would make sure that we can actually infer that B and C are also connected. And this is the kind of reasoning we can use with spatial ontology to either detect inconsistency in spatial data sets or complete knowledge, like infer additional relations that are not explicitly stated. And this is actually, some of these relations have been integrated in some of these data standards, like simple features and geospatial now have the RCC relations and other topological relations that allow us to query data sets using, for example, the topological relation of intersection or containment or parted on top of geometric data. We cannot yet reason with this kind of information directly in spatial databases or like knowledge graphs, but we can at least kind of extract information using that set of spatial relations. So some of my work, I've actually extended some of these ontologies also to multidimensional space, where we're dealing with 3D objects as well, where the arrangement in the 3D space is even more complicated. I'm just putting some pointers here. The idea is you need at least another primitive to kind of make this work. You cannot do this with a single primitive relation like off contact or parted. So one approach is to use something like relative dimension to kind of compare, saying that a point has a lower dimension than a line, or you can use something like boundary containment to kind of distinguish whether something is in the boundary or somehow else inside another object. And that actually allows us to integrate the spatial relations with the geometric representation that we have from simple features. So it allows us to logically reason together with geometric and qualitative relations. So, but kind of coming back to the different kinds of qualitative relations, one of the problems there is that a lot of these kind of relations that we use in everyday language are super vague and ambiguous, like connected to, even contains, between, or things like even is north of, sounds pretty precise, but leads to a question of what do you really mean by it? And that's where we can look at different axiomatization of the same relation, or like actually define ontologically different relations that just happen to have the same label in everyday language. So for example, we tried this out with the cardinal direction relation. You can think of the north of like everything that's the northern half of something, or something just the northern quarter, and so on, depending on how fine-grained you go with your direction labels. And so these are essentially, each of these like granularities define an ontology by themselves. And often the more difficult part is actually figuring out which of these ontologies are you using in a particular context. So you can think of like something like a linguistic statement borders north as really being translated logically to a disjunction of, well, it's either borders, it's kind of in the northern half, the northern quarter, the northern eighth, or so on. And then you have different axioms for each of these formal relationships. So far, I've kind of focused mostly on the spatial relations, simply because that's a big interest of mine. But there's also a whole another set of questions that arise. What are the spatial objects that we're talking about? So one distinction we can draw is what I sometimes call abstract spatial objects, like the mathematical abstractions, like points, lines, areas that we deal with in geometry, that are not objects, like material objects in their own right. But then we have also what we sometimes call physical space, like physical objects that are also related using the spatial relations that I just mentioned, and that actually have a location, have a size, so have like spatial qualities. And so typically the physical space view is closer to how we perceive space in our world, because we perceive like objects, not geometric objects. But it makes it a little more difficult to deal with kind of more abstract statements. So as it turns out, a lot of the top-level ontologies actually allow both kind of objects and relate them in some way. So for example, GFO has a very fine-grained distinction of different kinds of spatial objects based on their dimensionality, very similar to simple features. I will not talk much about that. It's probably another talk by maybe Frank. But I will just give a brief overview of how Dolce and BFO kind of deal with the spatial object and the duality, like the distinction between physical and abstract object. So this is just kind of a snapshot of the taxonomy of Dolce features. And so we have like endurance here. And then on the other side, we actually have like quality, spatial location being one of them. And then we have endurance having qualities. So we're saying they have a spatial location, and the spatial location takes on a particular value, namely a particular region. So we can use this construct to actually talk about changing locations as meaning the quality location of an object changes in its value, namely it occupies a different region of space. So endurance and perdurance also have qualities with spatial location being one of them. One interesting thing is there's a notion of feature that actually captures kind of things like boundaries, surfaces, like these kind of more abstract things. Well, there's actually debate whether these are abstract or physical, whether the boundary itself is a physical thing or an abstraction, but this is where Dolce put them as one of the physical endurance. So BFO does a slightly different approach. So we have material entities here, but we don't have like spatial region being somewhere else. They're actually also classified as just immaterial entities. And then we relate them directly, like material entities are located in some three-dimensional spatial region. And just like Dolce had a way to deal with features, BFO deals with features as other kinds of immaterial entities, like sites and boundaries here that can actually be of lower dimension. So these are things that are located in zero-dimensional, one-dimensional spatial region. And then
Torsten,
sites are three-dimensional again.
Torsten, you have very few minutes to finish.
Yes,
Sorry.
yes. Let me skip this actually. So the very last thing here, immaterial space. I talked a little bit about features already. A very interesting study is the nature of holds and other superficialities. So I can highly recommend that book. As I said, in Dolce, there are features. In BFO, like a hole, the donut hole would be a site, but both allow kind of representing the dependency on a material object. So to kind of summarize, we have kind of different kind of spatial relations as well as spatial objects, like Boardman Hall, third floor, and we kind of use them in all kind of a mixed form. So when we really deal with spatial knowledge, we need kind of both qualitative as well as geometric space, and need to know, for example, the third floor, we all assume that it's above the ground in the second floor. Like if you want to reason with that, we need to kind of encode this kind of knowledge. And then we have like abstractions like the campus or a town that we deal with. But that also can be kind of denote real objects. Like we can say Orono is not just like an abstraction on the map, it's actually also a city like made of streets and bricks and building. So, and then we have like mixtures of qualitative and quantitative information, something like 211 miles northeast of Boston kind of uses both, and is one of the most difficult statements to kind of make sense ontologically. So thank you. I hope you found this talk interesting, and I'm happy to take any questions.